So what I'm going to cover today, we're going to basically be talking about functions and its first and second derivative and kind of how they're all connected to each other. So we're going to talk about what a derivative tells us about a function, what the second derivative tells us about the function, and then we're going to do some practice with finding critical values and points of inflection. And then also, if you have your graphing calculator at home, I'm going to do one graphing calculator problem with you so that you can kind of see how to use your calculator to find some of this stuff. If you don't have it, it's going to be towards the end anyway, so you can take off or you can just follow along. It doesn't really matter. You'll be able to see mine on the screen, ideally. So let's start from the beginning. So I don't know where you guys are in your classes right now. I know that my class has talked a lot about the first derivative and what it tells us, but we haven't really talked much about the second derivative yet. So wherever you are, if you're seeing something that, oh, I haven't learned that yet, can you slow down a little? Just send me a little message in the chat and I'll be happy to do that for you. So the first thing I want to talk about is what the first derivative tells us about a function. So hopefully at some point earlier in this year, you talked about defining the derivative, right? And you probably did this big, long limit definition where you talked about that what you're doing is you're finding 2 points and you're finding the slope between those 2 points. And that was great back in Algebra 1. But now we want to know, since we don't have a straight line, can we get those 2 points really close to each other and maybe find the slope at a single point? So we started defining the derivative as the slope of a function at a single point, or the slope of the tangent line to a function at a point. And so that's what we're going to start talking about. And how is that helpful to us when we're talking about graphs and we're talking about data? So if the derivative is slope, okay, then it should make sense that if a function is increasing, right, then the derivative is going to have something important to tell us too, right? So if the derivative is greater than 0, that's a pretty good hint. That means the slope is positive, right? Greater than 0 means positive. So if the slope is positive, then the function is going to be increasing. And on the opposite side, if the derivative is negative, then f of x is decreasing. So knowing something about the derivative also tells us something useful about the function. We've got a few other things because the derivative could be positive, the derivative could be negative, but the derivative could also be neither, right? It could be either 0 Now, if the derivative is 0, that doesn't really tell us a whole lot all by itself, okay? But some more information could help us a little bit. So if the derivative is 0, that means we have a horizontal tangent, right? So our slope is 0, we have this horizontal tangent. So one of three things could basically happen. You could either have a maximum, right? A minimum, or potentially you could have something where it kind of evens out for a second here, but that it's not a maximum or a minimum, right? The function kind of keeps going after it takes a second to slow down a little bit, right? So we need to ask ourselves, well, how do we know the difference, right? In the first case, if you have a maximum, think about what's happening here, right? The function is increasing and then it's decreasing. So that means that f prime of x would change from positive to negative. So because our function starts out increasing and then decreases, if you're looking at f prime of x, you should see that the derivative is positive and then it becomes negative, right? So that's how we would know that it's a maximum value. If the opposite is happening, right, if f prime of x changes from negative to positive, then we get the minimum, right? Because we have a decreasing function here and then an increasing on the other side. If f prime of x doesn't change at all, if it stays positive on either side, like that third picture I drew, or it stays negative, then we don't have either positive, we don't have a maximum or a minimum, right? We have kind of something else going on. So these first two, the maxes and the mins, we call those critical values. They're important to us because they tell us about a change in the function. The other thing that could happen is that f prime of x could be undefined, right? So, and having a slope that's undefined, remember from Algebra 1 means you have a vertical tangent, right, up and down. So that happens in a couple different cases. It could happen where you have a, what we call like a cusp, right, a point, a corner, or you could have a discontinuity in your original function. So if the actual function itself is discontinuous at a point, then its derivative would also be most likely discontinuous at that point as well. So those three things, there's a bunch of different things that could happen if your function is undefined. So all of that to say, now what does that tell us about the second derivative? What does the second derivative tell us about the first derivative? So my class hasn't done second derivative much at all. So they don't know this yet, so you may or may not. But if you have a second derivative, theoretically, its relationship with the first derivative is the same as the relationship between the first derivative and the original function, right? So we just said all of these things about the first derivative telling us about the function, that if the first derivative is positive, f of x is increasing. That same thing is going to be hold true here, right? So if the second derivative is positive, then the first derivative is increasing. Because the second derivative is the slope of the first derivative. So that relationship is going to remain the same. If that second derivative is greater than 0, then the first derivative is going to be increasing. Now our next step is going to be to say, well, what does that mean in terms of the original function, right? If f prime of x is greater than 0, then f prime of x is increasing. If the slope of the original function is increasing, that means that the slope is getting bigger faster. So it's kind of like a second change, right? The change of the change. So your slope is getting steeper. Your slope is increasing. Your slope is getting steeper. Same is true with the rest of it, right? If it's less than 0, then f prime of x is decreasing. Same with 0. Now it's a little bit different with 0. Not really. In the next level it will be. But if f double prime of x equals 0, then f of x is going to have a max or a min, or potentially neither, in the same three cases that we had before. But what I don't want to spend a lot of time on that because this is exactly the same as what we did before. I want to now make the jump with, okay, what does the second derivative tell us about the function, right? So we talked for a second there about what happens if the second derivative is positive, right? Let's start with that one. We said that the first derivative is increasing. And what that basically means is that the slope is increasing, right? The slope is increasing. There's two kind of scenarios that could happen in. The first scenario is with the positive values, like comes naturally, right? The slope is increasing, so you're starting out shallow and you're getting steeper and steeper and steeper. So you get something that looks kind of like that. the natural way to think of it. The other way to think of it's a little bit harder because it's with negative numbers, right? So if I have a negative slope, but my negative slope is increasing, that actually means kind of the opposite, right? Those would have been nice if those met together, right? So my negative slope is increasing. Negative 10 becomes negative 3, becomes negative 1. So it actually looks less steep, right? So you're kind of coming down in it. The negative steepness coming down. So if the f double prime of x is greater than 0, f of prime of x is increasing, which can mean either of those two things. But either way, it means that the function is what we call concave up. So that's the word we've used to kind of describe that idea that the slope of the slope is increasing, right? Either in the negative direction or in the positive direction. But either way, you get this kind of like U shape going on. So that's what it's easy to remember. Concave up gets you a U. Okay. In the other direction, f double prime of x is less than 0. Then f prime of x is decreasing. In positive land, which is easier to understand, right? You're going to look something like that, right? You have a steeper slope that's getting less steep because your slope is decreasing. Your slope is becoming less steep. In the negative land, it would go the other way, right? So the negative values are decreasing. They're getting more negative. So you're getting steeper, but in a negative direction. Sorry, I did that backwards. I said it right and wrote it wrong. Let's do it this way. So there's our picture here. Sorry about that. So this is concave down. So if the second derivative is less than 0, you've got kind of a concave down type of shape going on in either direction. If the second derivative is 0, then that means the slope has max or min. Okay. And we call this, I'm running out of space here, a point of inflection. And it could mean that the concavity changes, right? It changes from concave up to concave down, or it could mean that it doesn't, but that you kind of have a point where you're leveling off for a second. So let's actually look at this in practice, because I think that makes it make a lot more sense. Okay. So I have a graph here, and I want to draw some conclusions about it. Now, the thing about graphs is there's going to be some things we can draw conclusions about and some things that we can't. And that's okay, but let's just try to see what we can draw conclusions about. So this is a graph of a function, f of x. And so I want to know, what do I know about the first and second derivatives of this function? And there's actually kind of a lot you can tell. So the first derivative tells us about slope. So we're going to start thinking about slope here. So what I like to kind of do is I want to make some scratch work here, and I make it kind of look like a number line. So I'm going to match my number line to the graph here. And this is going to be my f prime of x number line. Okay. Now, just to clarify up front, if you're taking the AP test, these number lines don't count as justification for anything that we do. They're just kind of scratch work. So if you like this method, and I recommend it, it works well, go for it, but just keep in mind that you need to also be writing out what you're thinking, not just leaving the number line, because this is not adequate defense for your response question. So f prime of x. So there's a couple things we know, right? I always like to start with f prime of x equaling 0. Those are the easiest points to find. So when does the slope of the function equal 0? So go ahead and look at that graph and tell me when you think the slope of the function is equal to 0. So hopefully you saw 3 locations here. Nobody really answered me, but hopefully you can still hear me. That there's 3 locations where the slope of the function equals 0, right? At that maximum right there at x equals -4, and the other maximum at x equals 1, and then also at that minimum x equals -2, the slope is now a horizontal tangent at those points. So that means that if the slope is a horizontal tangent there, then my derivative equals 0 there. So I know that on my f prime of x that I have a 0 at -4, at -2, and at 1. And those are the 3 places that f prime of x is equal to 0. What else can I know? Well, I also know that if the function is increasing, then my derivative is going to be positive. So in this first section right here, my function is increasing, right? I'm moving up. So my function is increasing between -infinity and -4. If my function is increasing in that interval, that means my derivative is positive. Then from -4 to -2, I'm now decreasing, right? I'm moving downward. So my derivative is going to be negative. Starting at -2, I'm increasing again. I'm moving upward, so I'm increasing. My slope is positive. Since my slope is positive, my derivative is positive. And then from 1 to infinity, I am decreasing in my function, so my derivative is negative. Now, if I were going to defend this on an AP test or a free response on my test in class, I would probably say something like, since f of x is increasing between -infinity and 4, f prime of x is greater than 0. Okay, so that might be a defense that we use in writing it out, right? The number line itself is not good enough, but what we said while we were making the number line is what you would write down if it asked for defense for why you know that's true. Okay, so now we know when the first derivative is positive, negative, positive, negative, right? What we don't know about the first derivative is exactly how high and how low we go. That's not information we have without giving me the function. If I had the function, I could figure that out, but I don't. So I'm a little bit limited. But what I can do is get a rough sketch, right? Because I know that my first derivative is going to have a 0 at -4, a 0 at 2, and a 0 at 1. And that before -4, I'm positive. Between -4 and -2, I'm negative. And again, I don't know how low that goes, right? And I also don't know exactly what the steepness of that is. I don't have enough information to tell that, but I can get a general idea. And then from -2 to -4, my derivative is positive again, so I'm above the x-axis. And then from 1 to infinity, my derivative is negative again, so I'm below the x-axis. So you get something that looks roughly like that, right? Again, not precise or specific, but a general shape is what that would look like. Now, hopefully you might also be thinking that my original function looks like it may be a quartic function, and my derivative looks like it may be a cubic function. We don't actually know that. That's not given information, but it certainly looks like that could be, and that makes sense to us too, because we already know that the derivative of something x to the fourth, right, is going to be an x to the third. So at least our picture makes sense in that regard, if that were to be what this is, right? We can do the same thing for the second derivative. We have less information about the second derivative because our first derivative sketch is kind of iffy, but we can estimate and get a general idea of our second derivative. I'm just going to erase this for a second so I have more room. So let's talk about second derivative. So we know that our second derivative is going to have a 0 when the first derivative has a max or min, right? When the first derivative has a horizontal tangent. So we can kind of guess where that is, right? And this is going to be a guess because, again, our first derivative graph is not accurate, really. So we have to kind of guess, but we can get an estimate. And if this were an actual problem, you'd probably be given more information, or all you'd be asked for was the general shape. I might just be like, give me a general shape, and that is fine, okay? But I do know that I have 2 zeros, right? I have one, whatever that point is, and one at whatever that point is. And we can estimate them if we want. If I drew my shape perfectly, I think it would end up being roughly negative 3.5 and negative 0.5. But again, those are guesses, they're estimates, okay? So then before negative 3.5, my first derivative is decreasing, right? So my first derivative is decreasing, which means my second derivative would be negative. Between negative 3 and 3.5 and negative 0.5, my first derivative is increasing. So my second derivative is positive. And then from negative 0.5 on, my first derivative is decreasing again. So my second derivative is negative. Now notice I'm doing a lot of my first derivative is this, so my second derivative is this. It's really important when you write stuff like this out that you're labeling things. Don't ever use the word it. Don't say it's decreasing, so it's positive, because then nobody knows what you're talking about. Because we have 3 functions right now, right? We have the function, original function, we have the first derivative, we have the second derivative. So make sure whatever you're talking about, you're being specific. F prime of x is decreasing, so f double prime of x is negative. That allows us to have a general shape for the second derivative too. Again, we actually don't know where it crosses. We know roughly where it crosses the x-axis, but we don't know any bottoms or tops at all. But we do know that it's going to cross roughly right here and right here. And that before, from negative infinity to negative 3.5, the second derivative is negative. And then in the middle, it's positive. And then at the end, the second derivative is negative again. So we get something that looks like that, which would also be a quadratic if this was a polynomial, and it certainly looks like it could be. So that fits what we were thinking too, 1 less degree. All right, well, let's try another one. So this one is of the graph f prime of x. So I'm actually going to give you a minute, since I just did that whole first example for you. I want you to start to think about it on your own, okay? Try to see if you can come up with some conclusions. This time we're given f prime of x. So I want to know what you can conclude about f of x and f double prime of x. So take just a minute or two and, start making a list on your own and see what you can come up with. So let's check in and see where you are, at least with f of x, right? So if I were looking at, now we're looking at the derivative. So I think my students have the hardest time with making sure they're going in the right direction. So in their head, they know something's increasing, something's positive, and they're good with that. But making sure that you're going in the right direction is what you have to focus on. So we're now switching directions from what we did last time. Last time we had the function and we were trying to tell information about the derivative. Now we're going to go backwards. I have the derivative. I want to know something about the function. So I start by looking at my derivative all the way to the left, right? So my derivative actually starts out below the x-axis. So from here to here, the derivative is negative. Well, if the derivative is negative, that means the function is decreasing. So we have to go in that order. The derivative is negative. So if I was writing this out to defend it, right, I would say that since f prime of x is less than 0, then f of x is decreasing, right? A negative derivative means the function is decreasing. So between 0 and -2, f of x is decreasing. From -2 all the way to 1, my derivative is now positive. It's above the x-axis. So f prime of x is positive. So f of x is going to be increasing. And then starting at 1 all the way to 5, my derivative again is negative. So f prime of x is less than 0. Then my function f of x is going to be decreasing. And from 3 to infinity, we're above the x-axis. Our f prime of x is positive, so our f of x is increasing. So we can draw all of those conclusions, okay? In the last one, I didn't really talk about where the maxes and mins were, but we could have, right? We know that a max and min happens when the function is going from increasing to decreasing. So let's talk about that in this one, right? If my function is decreasing and then it starts increasing at -2, right? We have our decrease and then our increase. That means that we have a minimum at x equals -2. For a defense, if you were writing this out, okay, because remember that number line isn't good enough for writing it out, you would probably write something like f prime of x equals 0 and is changing from negative to positive. So f of x has a relative min at x equals -2. Okay. Maybe not so much shorthand. I'm going to write out negative, positive, relative, min, just so that you can make sure that the graders are sure of what you're writing there. Okay. But that would be the defense, right? The way we know that that's a min is because the derivative is equal to 0 and the derivative is changing from negative to positive. So our original function is going to have a relative min, okay? It's also going to have a max at 1, right? Because we're changing, the derivative is changing from positive to negative. So the function is changing from increasing to decreasing, right? Increasing to decreasing. So you have a maximum there at the top. And then at 3, the derivative is going from negative to positive. The function is going from decreasing to increasing. So you're going to have a min again. So that's told us a lot about our function, right? We know where the maximums are, where the minimums are. We know when it's increasing and decreasing. What we don't know about the function here is any y values, right? We don't know what the function is, and we don't have any indication of what the y values are. So making a graph in this case is going to be a very rough sketch because we could actually kind of move it up or down wherever we want. We don't know what the x-intercepts are or the y-intercept. So we don't really have a good idea of where this graph is. But we do know that it's going to look something like this, right? Decrease, increase, decrease, increase. We just don't have a good idea of where to put it on the graph, right? Without more information. All right, so that's what we know about the function. We can also know things about the second derivative, right? So let's think about the second derivative. So the second derivative is talking about the slope of the first derivative. So the slope of the first derivative, let's look at the graph here. So at the beginning, from negative infinity, my derivative is increasing, and it keeps increasing until it gets to the top, right? So my first derivative is increasing, which means my second derivative is going to be positive until I get to x equals negative 1. Okay, so now we switch directions again. And that's what makes this so hard. That's why people have trouble with this, is because you have to really think about what you're doing. And a lot of times I'm not writing a lot of it out, and it's honestly just because I don't love writing with the stylus, and so it gets old after a while for me. But like, it really sometimes helps to write it out every time, right? So you might want to just, even in shorthand, kind of write it out is, you know, I'm looking at f prime of x, right? F prime of x is increasing from negative infinity to negative 1, right? So that means that f double prime of x is 1, right? So then you ask yourself that question. And you get f double prime of x is positive. And so you might want to be writing that out every time just to keep it straight in your head, if that helps. If not, you can use the number line. That's how I like to organize it. But either way, sorry, I'm just answering this question here. I'm not good at multitasking. Either way, whatever you do, if you organize it by a number line or you organize it by words, whatever works for you, the words are going to what you need to show when it comes to actually doing the problems, okay? I just want to do a quick check and make sure, can people hear me, or am I talking to myself over here? Oh, good. Just got scared for a second that I've been talking to myself for 25 minutes now. Perfect. Okay, so we got that first interval, right? So from negative infinity to negative 1, our first derivative is increasing, so our second derivative is positive. Nice. Now let's go to the next part, right? So from negative 1 to 2, our first derivative is decreasing. So if our first derivative is decreasing, that means our second derivative is negative. And then at the end, we're going to go from 2 to infinity, and we've got some increase motion here. So our second derivative is positive. As a quick reminder, that x equals negative 1 and x equals 2 are called inflection points. Okay, those are basically when the second derivative will be equal to 0. And those are important points because it talks about a change in concavity, right? We now know that the first derivative, or sorry, the original function is concave up between negative infinity and negative 1. And then concave down between negative 1 and 2. And then concave up again for the picture. So we actually could get a better picture maybe of f of x now. You can actually notice that what we drew originally kind of agrees, right? That we have concave up from here to here, and then concave down in this region, and then concave up again in this region. So our original picture kind of matches with what we found with the second derivative. All right, so I know this was originally scheduled 8 to 9. I'm going to go a little bit longer, so if you want to stay, you can absolutely stay. But I'm going to skip this one just because I want to get to something else, and I know that I want to go to bed at some point tonight, so let's move on for now. But certainly, if you want to go back later and look at it, you absolutely can, and I'll be happy to post the answer to that one too when I upload the video later on. All right, so here is a great example of probably not a problem you would be given on the AP test. You know, they're never going to say, tell me everything you know about anything, but we can kind of talk about all kinds of things about this function. So we were given graphs. Now we're going to work with an actual function. So the first thing that you would want to do is deal with the function itself. So important points in a original function are x-intercepts and y-intercepts. For time's sake, I'm going to give those to you, so because it's algebra, not calculus. So for the x-intercepts, you would have had to, it's a cubic function, and you would have had to factor out the x, right? And then you would have had to use a quadratic formula. It doesn't factor. So I don't want to go through that because that takes a long time, but I will tell you that you get 3 intercepts, one at 0, 0, and then it's -3 plus or minus √5/2 are the other two. Okay, so again, that would be quadratic formula. You guys, hopefully you can do that on your own at a later time. And then the y-intercept is 0, 0. So if we had more time, I would have let you do that, but we're going to kind of move on to do the calculus part. So the next thing we want to do is we want to say, okay, well, now we know where the x-intercepts and the y-intercepts are. I can kind of plot those if I wanted to. So we got a 0, 0 here. The other intercept is a little bit bigger than 2. And a little smaller than -4. So now we want to know, is the function increasing? Is it decreasing? Is it positive or negative? What else can I know about it? Okay, so that's when we're going to use the derivatives. So I'm going to start by taking f prime of x. So f prime of x, right? We use our power rule here, so we get 3x squared plus 6x minus 9. And I worked really hard to make that a nice pretty one that we can factor, because our goal would be to find where the derivative equals 0. Where the derivative equals 0 is going to tell us where our maxes and mins are, and it's going to give us points to look on either side for increasing and decreasing. So I'm going to set that equal to 0. And factor. So now we have the two places where f prime of x equals 0. So if f prime of x equals 0 at those 2 points, I now want to know what's happening on each side. Now here's the nice thing. Those are the only 2 places that f prime of x equals 0. So those are the only 2 places where we have a possible max or possible min. There's no other maxes or mins in this function. So that's great information to have. The only 2 places with zeros, the only 2 places we can have a max or min, which means whatever's happening on either side is going to be strictly increasing or strictly decreasing. So I can pick a number to the left of -3. I can pick any number I want. And if I plug that number in, that's going to tell me whether or not the function is increasing or decreasing for that whole section. So I can pick like -1,000,000, right? And I can go back to my derivative here, and I can say, I usually like to plug it into that step because as long as it's right, that kind of gives me an easier math to do than squaring things and above, okay? So if I plug in -1,000,000, right, I have 3, that's positive. -1,000,000 plus 3 is some really negative number. -1,000,000 minus 1 is also a negative number. So I have 3 is positive times a negative overall gets me a positive number. And I know that everything in that interval is going to be positive because the only time the derivative equals 0 is -3 and 1. So I can't magically jump from positive to negative unless I'm not continuous, right? But if I'm not continuous, then that would come out in the domain of the function or the domain of the derivative. We have polynomials here, so we know that they're continuous. So I also need to check a number between -3 and 1. 0 obviously is the easiest one, okay? But it doesn't matter what you pick. It could be anything in that interval. You plug in 0. You have 3 is positive. 0 plus 3 is positive. 0 minus 1 is negative. So we have positive, positive, negative. Derivative is negative. Then I need to pick a number on the other side of 1. I pick 1,000,000. Pick whatever I want. 3 times 1,000,000 plus 3, positive. 1,000,000 minus 1, positive. 3 positives make the positive. So I now know that my function is increasing, decreasing, then increasing, that I have a max at -3, right? And a min at 1. We can do better this time though, because now we have y values to work with, right? So I want to know exactly where that maximum is and exactly where that minimum is. So I know that my max happens when x equals -3, and my min happens when x equals 1. And I can go back and I can plug them into the original function to get my y value, right? I take that -3 and I plug it in, and I get my y value, which is 27. Okay, again, I know I just don't want to keep you guys super long time, so I'm going to do some of that math in my head. Well, I wrote it down earlier, but do some of that math for you. Okay, so -327. And then the minimum, so if I plugged 1 into the original function, right, I would get -1,6. Now we're plugging, sorry, -6. We're plugging into the original function because we want the y value. The derivative tells us where the minimum and maximum happens, but you don't want to plug those numbers back into the derivative because that doesn't tell you anything. Well, it will. It'll tell you it's 0 because that's what we solved for. You want to plug them back into the original function because that's the y value that you're going to plot. So we now can add to our graph that we have a minimum at -3, -6. And sorry, did that wrong. We have a maximum at -327 and a minimum at 1, -6. And I don't really have a scale here because I don't have a lot of room, but we should at least label it so we can tell what they are. Okay. So we have a max, we have a min, we have x and y intercepts. So we actually already have a pretty good idea of some connecting points, important points in the function that can get us a pretty good graph. But we can do even better because we can come up with the second derivative. So the second derivative here is going to be, let's see, 6x plus 6, right? So I'm taking the first derivative and I'm taking another derivative. Again, we're going to set that equal to 0. And so this tells us that we have an inflection point at x equals -1. And again, we can find that y value if we want, okay? So we can then go back and plug 1 into the original function and find, I don't know where I wrote it down. Guess we have to do it because I can't find where I wrote it down. So we're going to plug -1 back into that function. And we get, let's see, -1 plus 3 plus 9, 11. Did I do that right? I hope so.
9, 11, my favorite number.
So -1, 11 is our point of inflection. Okay. So now we can kind of connect the dots to make our picture. So we're, let's make our little number line for this one. Before -1, if I plug in 0, let's plug in 0 because that's nice and easy, right? We get 6 times 1 is 6, so that's positive. Hold on. Can't plug in 0, wrong side. Plug in -1,000,000, you get a negative number here. Plug in +1,000,000, you get a positive number here. So you have concave down, then concave up. So let me just go through that a little slower because that was messy. To kind of find out if we're concave up or concave down, we're going to plug some numbers into our second derivative to find out if the second derivative is positive or negative, right? So I plug in a number much smaller than -1, I get a negative number times 6. So that's where the negative came from. If I plug in a number bigger than 1, I get a positive number times 6. So I get positive. When the second derivative is negative, our function is concave down. When our second derivative is negative, our function is concave up. So that means we have kind of an upside down u at the beginning and then a right side up u at the end. And you can kind of see that happen, right? So at some point I have to cross the x-axis here, and then I'm going to go all the way up to my maximum and then back down. And this whole thing should remain an upside down u until I get to that red point. That's our point of inflection. That's when I'm going to start changing from the upside down u to the right side up u. So it's not always obvious graphically where that happens, but at some point we're changing from that upside down u to that right side up u, and we get something that looks like that. Okay. So we got a lot of information. We have 1, 2, 3, 4, 5, 6 points that are definitive. We have a rough idea of the direction of the graph. We know when it's increasing, when it's decreasing, when it's concave up, when it's concave down. That's a lot of information that we can glean just from having that original equation now. All right, so let's try this one. So this is a calculator active question. And so I'm going to take a second and hopefully not break anything by switching over to my calculator screen. So you're not going to be able to see this problem anymore. So if you have paper, what you want to write down just so you can see it is the function. So it's f prime of x equals sine of 1/10 e to the x. So write that down. And we're also only going to look at it between x is 0 and 5 because this function, you'll see in a second why we're restricting that domain. It goes on forever and has lots of zeros. Okay. But so what we're going to do is we're going to find some relative maxes and mins and then talk about how we know. And I'll show you how to do that on your calculator. Okay. So if you have that written down, I'm going to switch. I don't know how to do this. Let's see. Don't know that it's going to work. Okay, there we go. All right, yay. Okay, so there's my calculator. So I have the TI-84 plus here. Obviously, if you're using the Inspire or something different, it's going to be a little bit different. So you're going to have to kind of follow along with that. But kind of, I'm going to show you, at least if you have a TI, you should be able to find it somewhere kind of similar and do it with that. So the first thing I always recommend, especially if you have a free response question, you're going to have multiple parts and they're all going to be about the same function. So your best bet is to go into the y equals bar and input your function. Because by doing that, then you can use it as much as you want, right? So ignore all that. So you're going to do sine. And then it's 1/10. Actually, let me go back. I'm going to just put parentheses in there just to be safe. And then E